Let's now take a closer look at the binomial probability distribution, and specifically, let's take a look at actually calculating some probabilities. Now, as an example, Michelle steps to the free throw line, and she's going to take 13 shots. Historically, she's been hitting 78.3% from the free throw line. We want to calculate various probabilities regarding how many successful shots she will have. Can we use the binomial distribution to reasonably calculate those probabilities? If we can, we need to specify why. Okay, and the answer is yes. But remember those four things that we looked at earlier? The n independent identical trials and so forth. We can't just simply say yeah. We need to justify why. So let's take a look at these one by one. The first assumption, and these are the lists of assumptions. Whenever you use a distribution, you should always list the assumptions and show how this scenario satisfies those assumptions, at least reasonably satisfies them. It doesn't cut it to simply say there are n repeated independent and identical trials. Okay, yeah, that's assumption for a binomial, but why is it that this scenario has n repeated independent identical trials? You need to make that connection. They're repeated. It's repeated, yeah, she's going to shoot. Let me change colors here. I'm going to need a different pen. They're repeated, yeah, she will shoot 13. She's just going to free throw line, shooting 13. If she hits the first, that does not tell us about the next. I just justified the independent. And they're identical because she's just shooting. See, we don't have to go in and write a dissertation on this. It's just briefly, why is it that we think that these are satisfied? She's going to stand up, go up to the free throw line and shoot 13. Okay, she's just going to repeat the shots. Okay, so there's my n repeated. I'm going to do it n times. N is 13. N is fixed. And she's just going to sit there and shoot. So it's identical every time. We're not changing. It's not like we're going to shoot one, then have somebody stand in front of her and jump up and down and try to block the second one. That would definitely not be identical. They're independent. If she hits the first one, that doesn't really tell me what's going to happen the second time. We're going to reason that out. That's a reasonable thing to assume. Okay, there are only two possible outcomes for each trial. We're going to label one a success and one a failure. Well, that's true. I'll simply say a success equals she hits, and a failure equals a miss. That's it. That's all that can happen. She's either going to hit or miss. That's it. Remains constant for all trials. This is reasonable. Historically, she's been hitting, I need to go back. What was it she's hitting? Oh, 78.3%. 0.783. So historically, that's what's been happening, so it's reasonable to use that. Now, do you think it's truly 100% accurate? Probably not. You know, what if her shoulder's a little bit sore today? Or what if she didn't sleep well last night? Or what if, there's 1,000 different what ifs. But let's be realistic. Like I said earlier, the mathematics is exact, but the application is not. It's reasonable to assume about 78.3%. You watch baseball, and when a batter comes up and they say, well, God, this guy's been hitting 305 this season. You're thinking, hey, this guy's a good hitter. 305, that's pretty good. So you're thinking probability is about 0.305 that he's going to hit again at this time, right? Well, maybe not. Maybe he had a bad day. You know, all these things come into play. We don't want to get too esoteric on it, because if we did, you never ever use any of these distributions. And these distributions are used to help come to informed decisions. So we're okay here. The 0.783 seems pretty reasonable. Now, the random variable records the number of successes and n trials. I'm just going to say x equals the number of hits. Okay, I'm going to use x as the random variable. You could use h for hits. Who cares? Whatever. All right, let's go ahead and actually work with some probabilities now. Here's the same scenario, and the first question is find the probability she hits exactly 9. Now, what I tell my students to do is, I really think it's a good idea, number 0 through 13, so 13 shots. The 0 would be no hits, 1's 1 hit, 2's 2 hits, so forth. And she hits exactly 9. Draw a circle, make a box, whatever, around that part that signifies or represents this particular scenario, this particular question. The probability statement is probability x equals 9. This is exactly 9. Now, the reason that's important is because in your calculator, when we start doing probabilities, you have two options. One of them is binomial PDF. The other is binomial CDF. The PDF, probability distribution function, will calculate the probability of exactly this many successes. CDF is cumulative. The CDF starts at 0, finds a probability of 0, adds it to the probability of 1 success, adds it to the probability of 2, keeps on going until you tell it to stop. So if I use CDF of 9, it'll take the probability of 0 plus the probability of 1 all the way up to and including the probability of 9. Add up all those probabilities. Now I know if I do CDF of 13, that's going to add up all the probability for all the possible outcomes, which we know is going to be 1. Okay, so I'm going to change this probability statement here just a little bit because it makes sense to. I'm going to say this is the probability x equals 9. She hits exactly 9. Given, I'm going to add the additional information. Given n equals 13 and pi here is going to represent the probability of success, equals 0.783. Now the reason I added that is because these two pieces of information right here completely specifies the distribution. If I know n and I know pi, I can calculate any probability you could possibly ask me about that particular binomial. That's all I need. Start far and away. Ask questions. I can sit here all day long and answer every single thing for you. That's all I need to know. So I'm going to add that to my probability statement so I have everything collected all together there. All right, this is asking specifically that there were 9 successes, so this would be a PDF. So I'm just going to cross out CDF. We will be working with the PDF. And I'm going to show you, I'm going to write down the notation here, and then I'm going to jump to the calculator and actually do it. You select binomial PDF, and the syntax is n, pi, and x. So in this case, it would be binomial PDF, n is 13, pi is 0.783, x is 9. Now, for my students, and I know there's students from other classes, other professors that use these videos, for my students, when you do a problem, you must show me this. You must show me your actual calculator command. For one thing, if you get the answer wrong, I can take a look at what you did and give you some partial credit. So this is important. This is what I think of as showing your work for this particular type of problem. So let's go over to calculator and take a look and actually do it. Okay. If I go to second, hit the second key, and down here, hit the distribution key. The distribution, there it is, right by the keypad. It says DISTR. It's above the vars key. Okay, vars and DISTR. Select that, and then what we get, I'm going to zoom back in. That's pretty good. What we get is a bunch of distributions. The first one that we see here says normal PDF, normal CDF. Well, that's not what we want. We're working with the binomial. So if I hit my up arrow key, it'll take me to the bottom of the list. And if I look at option 0 and option A, those are the two for the binomial. Option 0 is binomial PDF. So if you remember it next time, you go to second distribution, just hit the 0 key. It's going to bring up binomial PDF. Or if I'm doing a problem with a CDF, which we will do in a few minutes, then option A. So I'm going to select it by hitting enter. And there's the command pasted to my screen. Now all it's doing is it's waiting for me to give it the information that it needs. The information that it needs is n, which is 13, comma, pi, which is 0.783, comma, and how many successes were we looking for? Exactly 9. I'm going to close it up with a paren, makes it all nice and neat. Hit enter. There's my probability, 0.1754. So if she's been hitting 78.3%, and she goes to the free throw line right now to shoot 13, the probability that she's going to hit exactly 9 is a little over 17%, 0.1754. Okay, this equals 0.1754. All right, another example. It's the same scenario, but this time I'm asking what's the probability she hits less than 9. So my statement is going to be the probability x is less than 9, given, once again, n equals 13, pi equals 0.783. Now, go to my picture here. What's it mean to be less than 9? Well, that means I'm going to draw a circle or box, whatever, from 0 to 8. That means this is equal to the probability x is less than or equal to 8. Given that same information. Well, I should probably keep writing that just for consistency here. There we go. Okay, this is important because in my calculator, when I use the CDF command, PDF is no longer appropriate. I'm going to cross that out. PDF would give me a probability of exactly 9. Well, we just did that. We want less than 9. When I use CDF, the command is going to be binom CDF, n is 13. Well, let me write down here again. It's n, pi, and x, just like it was last time. Binom CDF, n is 13, pi is 0.783. X now, less than 9, is going to be 8. When I put in this number here, this is saying stop here, but include it. I'm going to stop at 8, but I'm going to include the probability of 8 in all that probability. It's going to add up 0 plus 1 plus 2 plus 3 plus 8, all those probabilities. So let's take a look at the calculator real quick and see what we get. This is the one we just did, binom PDF of 9. So now I want the probability is less than 9, which is less than or equal to 8. Go to second distribution. I'm going to hit the up arrow key and go to option A. Now it says CDF. N's 13.783. And I want to stop at 8. This is less than 9, which is less than or equal to 8. That is 0.1310. Okay. 0.1310. Well, you're probably thinking, no, wait a minute, how can that be? Look at the previous one. It was 17% for exactly 9, just one thing, but only about 13% for 0 through 8. How can that possibly be? Well, we're not going to do it here, but it would be a good exercise for you to do. Do the PDF on every single one of these. Every single one. You know what? Let's go back to calculators. Let's do that. I'm going to show you something kind of slick. Give me like this. Okay, I'm going to go to Stat, Edit, and I'm going to clear out a couple lists here. This is some stuff we did previously. So I'm going to go up to it and hit Clear. Now over here, I'm going to put 0 through 13. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so there's all my successes. Those are my X's. I'm going to go up to L2. Second distribution, it's my vars. Binom PDF. See, n equals 13. Pi equals 0.783. And x equals, well, what does x equal? L1. That's where all my x's are. Now, because L2 is highlighted, it's saying use this binomial command on every single one of these and put the probability right next to it. So I'm going to hit enter. If you see this little thing moving, that means your calculator was working. Now, look what we have here. The probability of none is 2.4 e negative 9. That's scientific notation. That's saying take that decimal point, move it to the left 9 places. That's 0.000000002. Guys, that's basically, it ain't going to happen. Well, heck, if she's shooting 78% historically, and she's going to shoot 13. Do you really think she'd miss all 13? No, that's what this is saying. So this probability is very, very, very small. Matter of fact, it's not up until you get to probability of hitting 5 that we even see a number we'd recognize as a normal number. That's 0.0019. I can move down a little bit, and let's see here. There's my 7. There's my 8. There's 9. There's a 17.54%. So see, all these probabilities are very, very small. When I add them up, I just get something that's still kind of small. And then I'm getting bigger as I go along. And at some point, see, here the probability of getting 10 has the most. It's 25%. Then 11 starts getting smaller. 12 is smaller. Hitting all 13 is also not very likely. So you can get an idea of how the probabilities are distributed there. So it makes sense in this case, because the probability of success is so high, that if I sum up 0 through 8, that I actually get something less than simply looking at 9. Okay. Here's another example. Same scenario, but I want to look at the probability she hits more than 9. Well, this is the probability x is greater than 9, given that same information. N is 13, pi is 0.783. Well, what does more than 9 mean? Well, more than 9 is going to be 10 through 13. Well, this sounds like CDF, and it is. I'm going to get rid of the PDF, cross that out. We will not be working with the PDF here. Although we could. If you did the PDF of 10, added it to the PDF of 11, added it to the PDF of 12, added it to the PDF of 13, you would get the right answer. But there's an easier way to do it. Well, unfortunately, the CDF starts at 0 and keeps going until I tell it to stop. So I can't tell it to start at 10 and stop at 13. But I do know if I add up all of these probabilities, if I add up all of them, it's going to be 1. If I add up all of them, it's going to be too big. What is it too big? It's going to be this much too big. Oops, I need to do that again because I kind of cut my 9 in half. There we go. So I can look at it this way. The probability that x is greater than 9 actually equals 1, the whole thing, minus the probability x is less than or equal to 9. See, that's why this picture is so important. Remember, CDF starts at 0. You tell it where to stop, and it's going to include that point. I'm going to stop at 9. That's where it ends. The piece ends. That's too big. Well, if I subtract this off, what am I left with? 10 through 13. So how can I do that in a calculator? I would literally just type in 1 minus binom CDF 13.7839. This piece right here will give me that red piece, and it's subtracted off. All right, let's take a look at the calculator and do that. Let me get out of here, clear that out. Okay, second distribution, binom CDF. Whoops, wait a minute, I messed that up. Start that again. I want to do 1 minus. Now look at your keypads. There's a negative sign in parentheses on the bottom. That's for a negative number. That's not minus. On the right-hand side, you see the division, the x for multiplication, then the minus. That's actually subtraction. That's the one you want. So second distribution, binom CDF. So you have 1 minus what I'm about to do here, 13.783, and we said 9. Hit enter, and there it is, 0.6936. So this is equal to 0.6936. Again, if you did these individually, added them up, that's the same answer that you're going to get within rounding. Okay, if you start rounding, you may be off in the thousands or 10,000th place or something like that. Okay, let's see. What do we have coming up here next? All right, she hits from 4 to 9. What does that mean? Well, it means start at 4 to 9, go to and include 9. So if I'm going to draw my box, this is going to be 4 to 9. My probability statement would be the probability that 4 is less than or equal to x, which is less than or equal to 9, given all that same information, n equals 13, pi equals 0.783. Now, how can I do this on the calculator? Well, again, I don't want to use PDF. I could use PDF. Take the PDF of 4, add it to PDF of 5. It's kind of a long way around, but yeah, I could do that. But notice if I take the CDF of 9, if I do binom CDF 13.7839, that's going to give me the probability from 9 all the way back to 0. It's too big. How much too big? 0 through 3. So if I subtract from it binom CDF 13.783, and where do I need to cut it off? At 3. That will subtract off the piece that's too big. That will give me my answer. So let's go ahead and take a look at the calculator and actually do it. I'll clear this from the last one. Go second distribution, binom CDF 13.783. That was 9. I'm going to go all the way up to and stop at 9. Minus second distribution, go back to binom CDF 13.783, comma 3. Go subtract off the probability of 3 or fewer. Hit enter. There's my solution, 0.3063. So this is equal to 0.3063. There's my solution. Now, in terms of the probability statement, I can write this as the probability that x is less than or equal to 9 minus the probability that x is less than or equal to 3. This right here is exactly what I did down there with the binom CDF command. Okay, one more example here. Same scenario, but this time probability she hits between 3 and 11. My probability statement is going to be the probability that 3 is less than x, which is less than 11. Given the same information, n is 13, pi is 0.783. Okay, between. So my box would be, okay, what's between? That's from 4 to 10. So this is actually the same thing as saying, okay, what's the probability that 4 is less than or equal to x, which is less than or equal to 10, given all that same information. How do we do this? Well, it's the exact same thing as we just did. The numbers are different, but it's the exact same idea. Again, I don't want to use PDF. I will use CDF. This will be binom CDF 13.78310. That's all of this. It's too big. How much too big? 0 through 3. Subtract off binom CDF 13.783, whoops, 3. Okay, go ahead and do that in the calculator. Yeah, let's go ahead and step over and do it real quick. Okay, this is my last command. You notice it was binom CDF of 9 minus binom CDF of 3. Well, because I'm going to use the same sort of thing again, I can hit second and then enter, and it brings up that last command. So I'm going to go up here and change this 9 to a 10. Type a 1, and before I stomp on top of that parentheses, I'm going to go second, and then above the delete key, you see INS for insert. Now this means I'm in insert mode. Put in my 0 for 10. And then I'm going to go down arrow, and I don't need to do anything else because I'm still using a 3. So here's a binom CDF of 10 minus a binom CDF of 3. It's very similar to the problem we just did. Hit enter, and there's the probability. It is 0.5595. There it is. Okay, that's going to wrap up this particular section. And the next one, we'll take a look at calculating the mean and the variance for a binomial.